He kōna e purangi tēnei nā te reo irirangi o Aotearoa.
Kia ora, and welcome to Elemental from RNZ, in which we're celebrating 150 years of the periodic table of chemical elements. I'm Allan Blackman from the Auckland University of Technology.
And I'm Alison Ballance. And in our alphabetical search for the what, when and where of chemistry, we have reached the Y's, in a manner of speaking. We have certainly reached the letter Y, which brings us to the long-awaited element Ytterbium, spelt, for those of you like me who have been until this moment blissfully unaware of its existence, Ytterbium.
And Ytterbium is a lanthanoid, named of course after the town of Ytterby, Ytterby, in Sweden.
And I think this episode will have a familiar ring to it if you have listened to the previous episodes about erbium and terbium, which were also named after Ytterby, as was yttrium, which is our next episode. I refer also to any previous episode that features a lanthanoid, of which there seem to have been more than enough, Alan. Anyway, tell me about this lanthanoid.
Okay, so vital statistics, elemental symbol YB and atomic number 70. And Alison, you are going to be thrilled to know that this is the last of the lanthanoid elements alphabetically.
I couldn't possibly cheer loudly about that.
And that means this is the last tortuous isolation procedure that we will be covering.
Thank goodness for that.
So the story starts with a porcelain factory founded in Stockholm in 1726, which later bought the mine in Ytterby, from which the previously mentioned elements were discovered. So ytterbium was extracted in 1878 from an impure sample of erbium, which itself was extracted from an impure sample of yttrium. And then, ironically, around 30 years later, the sample of ytterbium was shown to contain lutetium. Like all the lanthanoids, it's a metal that reacts with both air and water. And by the by, and we mentioned this rule in a previous episode, but as an even-numbered lanthanoid, in accordance with the Oddo-Harkins rule, ytterbium is significantly more abundant than its neighbours thulium and lutetium. There we go, folks. You may be asking what it's useful for. My answer, not a lot.
Oh well, let's just get it over with, shall we? What is it useful for?
Okay, so the best thing about ytterbium, in my opinion, is that until July this year, the most accurate clocks on Earth were based on ytterbium. Now, we talked about highly accurate cesium clocks in the cesium episode, and cesium clocks are, of course, the official time standard. However, two ytterbium clocks at the National Institute of Standards in the USA have an accuracy of better than 1.4 parts in 10 to the power of 18.
Whatever that means.
Well, I'll tell you what that means in a minute. But that is in fact 100 times better than cesium clocks. So this means that it's the equivalent of losing half a second over the age of the universe. I'm waiting for a wow.
My mouth is open. Can't you see it? I am impressed.
Yeah, well, so everybody should be. However, these ytterbium lattice clocks, as they're known, they're not exactly ones that you can stick on your mantelpiece. So they operate at 10 millionths of a degree above absolute zero. They involve 10,000 ytterbium atoms, which in fact is a very small number, believe it or not, held in an optical lattice made of laser light, and they generally take up a whole room. So, what these clocks can actually do, they can allow measurement of the distortion of space-time. And, in fact, they will respond to the change in gravity that occurs due to a 2-centimetre height difference, which is utterly mind-blowing.
They sound amazing. But I'm curious, what superseded them in July?
Well, the quantum logic clock. And this is perhaps best known for showing you age faster if you stand on a stool, believe it or not. And so this, in fact, uses aluminium and magnesium, and a single aluminium ion kept in check by a magnesium ion provides the clock ticks. It's only more accurate in terms of precision, while the Ytterbium clocks are still more stable over a longer period, but we might skip the finer details of that.
Okay, I'm happy to let that one go, but can you explain that bit about the stall, please?
Maybe. It's more physics than chemistry, but here goes. The clock is in fact so accurate that it was apparently used to demonstrate the time dilation aspects of Einstein's theory of relativity. That is, that time passes faster at higher elevations, but more slowly when you move faster.
Well, that was well done. Not bad for a chemist.
Yeah.
I think we should have a second of silence to appreciate the fine details of those clocks relying on single ions and single atoms to tell us about theories that explain how the universe works. Okay, that'll do. Although I do realise that my concept of a second is not nearly as accurate as an Ytterbium lattice clock, so that may have been a little longer than a second. Do you have anything else to report about Ytterbium?
Well, we're scraping here. Ytterbium finds use in lasers, while the Ytterbium 169 isotope can be used in portable X-ray machines. And if you recall back to the thulium episode, the thulium 170 isotope could also do this. And this is in fact very useful when you don't have any electricity around, because you can have X-rays any old time, any old place. So, a really interesting aspect of Ytterbium is that the metal changes its conductivity in response to pressure. So under ambient conditions, it behaves like a metal because it is a metal. But as the pressure is increased to around about 16,000 times atmospheric, it becomes a semiconductor, and its resistance keeps increasing until around about 40,000 times atmospheric pressure, when it suddenly starts to become more conductive again. And this property has been used in stress gauges, particularly those used to monitor the shock waves and deformations in earthquakes and nuclear explosions.
Crikey, that'll do. This episode of Elemental was entirely dedicated to the chemical element Ytterbium, apart from our little digression into quantum logic clocks. But that's because there's only so much we can say about it. But you'll find plenty more about other lanthanoids and clocks and so on in other episodes of the podcast at rnz.co.nz/chemistry.
Or you can listen to us on your favourite podcast app. Please rate and review us if you can, or help by spreading the word about us. It's never too late to start listening. We're back next week with the rather similar sounding Yttrium. But until then, I'm Allan Blackman.
And I'm Alison Balance. Kia ora mai.